I'll be presenting my paper titled mmSpy, Spying Phone Calls Using mmWave Radars. My co-author on this paper is Dr. Mahanth Gowda, who is my PhD advisor, and this research has been sponsored by Penn State and NSF. So we often share sensitive information over phone calls. Imagine your aunt or uncle calling you in and sharing their credit card details with you, right? You might imagine that such an interaction is fundamentally benign, but if somebody in your environment could just tap into your phone call and compromise your credit card data, it would be something very serious. All of this kind of broadly falls into the umbrella of wireless eavesdropping, and in the last session, Long Huang from LSU made a mention of wireless eavesdropping. mmSpy is a system that fits exactly within the theme. So how do we implement it? Concurrent to the development of 5G telecommunication systems, there's also been a lot of force put into developing radars that work in the same frequency ranges, roughly in the 28 to 300 gigahertz, and these are called mmWave radars because the wavelength of the waves that are used is in the millimeter range. They offer very high range resolution, high precision, and even sensitivity to micrometer level vibrations. Broadly, there are two major aspects of the mmSpy system. The first is the signal acquisition, which is done using mmWave radars, and there's also a machine learning component that we use to process the data that we acquire from mmWave radars. I will be explaining each of these components separately, and then I'll conclude by explaining how everything comes together. So first, let's talk about mmWave radars. In mmSpy, we use Texas Instruments millimeter wave radars. They broadly work in the passband ranges of 77 to 81 gigahertz and 60 to 64 gigahertz. These radars have found a lot of use cases already in various applications that include but are not restricted to automotive ranging in self-driving cars, smart health monitoring that includes respiration and heartbeat monitoring at a distance, and different forms of activity tracking that include, but again are not restricted to, gesture tracking, fall detection. Other than that, millimeter wave radars are also being explored in the areas of smart agriculture, material sensing. So the applications are all over the place. The way that TI's mmWave radars work is they fundamentally use a sinusoidal signal with a varying frequency component. These signals are commonly referred to as chirps, and the modulation scheme is known as frequency modulated continuous wave, or FMCW for short. As for the ranging, once a chirp is shot out from the transmitter antenna and it bounces off an object in the environment, we can subtract the transmitter and the received signals at the end of the receiver, and from that we can infer the distance to different objects in the environment. So the intermediate frequency at the receiver end basically is encoded with the difference in frequencies of the transmitted and the received signals. We do a Fourier analysis of that, and we can basically use this formula to estimate the distance to any object. The slope of a chirp is how fast the frequency is modulated, and we of course know the speed of light. So the intermediate frequency signal at the receiver has a frequency component of 2s times d over c. Now, when there are really subtle movements or really minute vibrations of the order of micrometers, the intermediate frequency signal does not show us a whole different frequency, but there are subtle phase changes in the signal. If we track these phase changes over time, we basically get an audio signal. Here's a representation of that over time. So the axis that's labeled as chirp index is analogous to time, and I'm just basically tracking multiple chirps over time. The distance bin is an index of how far away different objects are in the environment. In mmSpy, we assume that the signal of interest is always the most prominent signal, so the highest peak is corresponding to a phone, and we also see some spurious peaks, but these are from different people in the environment. It's from walls, it's from chairs, and a lot of other things. But we're able to satisfactorily isolate the signal that's bouncing off of a phone. We track these over time, we track the phase changes, and we can figure out what's being said over a phone call, even though it's at a distance. In principle, however, there are a lot of other considerations that need to be taken in before deploying the radars for this, and we provide a very detailed write-up on how we configure the radars to work this way. And please check out the paper for that. So a summary of the signal acquisition system is basically that we have radars that shoot out chirps. At the receiver end, the intermediate frequency signal has the distance to different objects encoded in that. We track the objects over time, we track the phases over time, we extract the phases and statistically correct them, and we're left with an audio signal. Voila. And now I'll move over to the second component of mmSpy, which is basically the signal analysis and the machine learning side of things. So what makes machine learning really nice? Well, it's actually the availability of a lot of training data. I do hear a few smirks, but thank you. However, in the area of radio analysis, a lot of times naturally available large-scale data sets are just not present. We can't find them. So the strategy that we take is we take existing audio data sets, we modify them to look like radio data sets, and we train our models on top of that and apply transfer learning on a small-scale radar data. So that's the overall strategy of data synthesis, as well as using transfer learning to adapt onto real data. The targeted tasks of mmSpy are an audio enhancement task, as well as a digit and keyword classification task. We begin the signal analysis pipeline by essentially filtering the audio, really old school techniques, but the number 4 is being spoken, and this is a spectrogram representation. What we observe is that when we extract the raw audio, it's extremely noisy. The fundamental digit that's being spoken is not very clearly visible within the spectrogram, or not even that well audible. But you apply a bandpass filter and a spectral subtraction filter, and we get a good starting point. Right? As for the training synthesis, the training data synthesis, we begin by analyzing different aspects of the real radar data. We try to understand how noisy the data is. We try to understand other aspects of the radar, such as the DC drift and certain other radar parameters. We basically transform the large-scale audio data sets into data sets that look like radio, and we adapt the final models to the small sample radar data. So what models am I exactly talking about? So the first task, which is related to audio enhancement, we use a unit architecture to enhance the audio. One nuance is that we use this architecture to enhance audio, and we also use a post-processing technique where we combine the output of this architecture with the input to form a masked signal, and we observe that that gives us the best quality. The other architecture is that we use spectrograms, usual convolutional neural networks with residual blocks to classify keywords and digits. So finally, the overall system looks kind of like this. We begin with existing data sets, we synthesize training data, we develop synthetic models, and on the plane of the real data, we track actual phone vibrations that are going on with the radars. We correct the data, and we form the audio signals. We adapt the synthetic models using transfer learning and domain adaptation, and the final model that we get after all of this is the model that we actually evaluate. The experimental setup is as follows. So the host computer is connected to the mmWave radar. There's an arrow that's pointing to the radar, and that radar is doing all of these chirp business. It's shooting out chirps into the environment, and they're bouncing off of objects in the environment, and it's coming right back at it. We also vary the distance to the phone. This is approximately 4 feet, but we'll go all the way to 6 feet. Just a little bit of a nuance for taking the photo, but we do cover a larger distance than this. As for the specific experiments, we've used 2 different phone models, 2 different radars. We have 2 different enhancement tasks and also 2 different data sets. So just take a combination of all of them, and the whole experimental suite is based on, kind of like a one-to-one combination of all of these different things. Okay, so I have given the overview of the mmSpy system, so now I would like to talk about the results. So at first, just want to talk about the audio enhancement results. So the first row in this visual is the raw sensor data. Basically, it's extremely noisy. We apply signal processing, and then we use the enhancement neural network to form the enhanced signal. And the good features of these audio are slowly becoming clearer, but then we combine this with the input signal all over again, which we call the enhanced plus masked signal, and that looks a lot closer to the true digits that are being spoken. Likewise, we apply the same architecture to a speech command data set, which is by Google, and we observe a very similar thing, that we start with very noisy radar data, but as you go down the pipeline, it gets better at every step. So I have a small sample output, and I'll play that for you. So that was the raw data, the raw data that we capture from the radar, and when we pass it through the enhancement pipeline, this is what we get. So that's an output of the audio enhancement pipeline, and quantitatively, we of course observe a really good improvement as the data is passed through the pipeline. So the dotted line on top is the mean square error between the true audio and the raw audio after normalization, and the ones at the bottom are the 2 different cases of just enhancement and enhancement plus combining with the original sensor data. And we see that, yeah, there is definitely a quantitative improvement. I'll quickly move over to the results of classification. We begin by analyzing how the signal quality deteriorates over distance. And naturally, as you go further and further away from the target phone, the quality of the signal, the SNR, goes on decreasing. Beyond 6 feet, it's almost unintelligible, but for this study, we just targeted 1, 2, 3, all the way till 6 feet. That's a representation of how the signal deteriorates. The accuracy that we observe across different cases is represented in this table. So the first 3 rows are the classification of digits being spoken over the phone with radars at the different frequency ranges, and the last row is the speech commands. We do observe that in the best case, the accuracy is roughly around 80%, which is quite concerning, but as we go further away, it really goes on decreasing, but nonetheless, any positive accuracy in any of these tasks is a dangerous thing. That's what I believe. As for the effect of domain adaptation and transfer learning, here's a representation of how well the data synthesis pipeline actually worked. So the gray bars are when we try to train the model directly on radar data, and the black bars are when we use a synthetic data pipeline and try to go over everything. Here's a confusion matrix of the audio MNIST test cases and the speech command test cases, and of course, a bright diagonal represents that the classifiers are working pretty well. Now the audio MNIST data set itself is tagged with user IDs, and we do observe that there's a fair variation in how well the system performs against each user. We have not done a detailed analysis in this, but broadly, there are different people from different cultures and different accents, and the system responds differently to all of them. And there are ways in which we will handle this. One of the comments that we received quite pertinently is, okay, you're doing this in a lab setting, so what happens when you actually make somebody hold the phone and you try to attack them? So what we observe is basically that muscular twitches, respiration, and all of that can cause spikes in the radar stream, but underlying all of the large magnitude noise, there's still some audio preserved, and we've presented these results in the paper as well. All right, so I'm almost at the end of my talk, and I want to go over some general challenges in implementing mmSpy that by and large we should, to make the whole system robust and more dangerous, we should try to train the model with many more phones, and as a consequence of which, try to account for different materials, new age materials that go into the building of phones. We also want to address motion where someone's actually moving around with the phone. So that's another step towards practicality. And as for speech and accents, just use larger scale models that go over automatic speech recognition. There are some defenses, of course. So firstly, it's important to understand that such an attack is possible. It's also good if we can develop materials that absorb vibrations instead of actually allowing them to permeate through the solid. And one good defense is if the speakers within your phone can be beamforming, so it directs all of the vibrations away from the back of the phone. All right. So future work is to basically address all the limitations in a nutshell. We're going to try to address the speech recognition part of it as well as the motion. And more broadly, we have developed a framework that helps us extract audio from radars. So with that, I conclude, and I'm at the end of my presentation.
All right, let's thank our speaker. Again, if you have questions, please approach the microphone and identify yourself and where you're from. While we're waiting for that, I have a question for you. Myself and many of the people here have, some kind of a plastic or rubber protector on our phone. Not because I'm clumsy, but because this does drop. That would seem to be a pretty good defense already, right? I mean, this doesn't seem to propagate the signal. Can you talk about that? Yeah.
So I haven't done a large-scale experiment on this, but that was something that I was really interested in as well. And my phone's not in my pocket, but even I have a really big case at the back of it. It doesn't make as much of a difference as you would think.
It doesn't make as much of a difference?
No, because the vibrations... For the defense aspect of it, it doesn't. So the vibrations can still pass through like modern materials that are being used as phone cases.
Do you have experiments for that?
I don't have large-scale experiments, and I don't have results on the paper, but I had done like a smaller scale experiment to do that, all right? So there was a batch of data that I collected that, in exactly this setting, but we didn't pursue it.
Okay. Thanks. Please go ahead.
Yeah. My name is Efrain Lopez from Texas A&M Corpus Christi. So just as a quick question. So first of all, great paper, great presentation. So if I understood correctly, you're getting the audio that the user is listening to in the phone, right?
Yeah.
Yeah. So that would be different from, let's say, if you have a microphone, like this is a much better way of spying than just having a microphone next to the person.
Okay, I think that's a really good point that you've brought up, and we do elaborate this on the paper, which is the fact that radars work on a point-to-point source isolation basis, whereas microphone picks up all of the signals in the environment. So the defense, if you have a microphone to do this sort of a thing, is just play a really loud noise in the environment. However, when you do that as like a primary defense against an attack like mmSpy, it doesn't work because it's like getting right at the source at one point, picking up the vibrations right there. Does that make sense?
Yes, yeah, that answers my question.
Yeah. Thank you for the question. That was a good question.
Jessica, if you want to go ahead and start setting up any more questions? One more. I'm gonna
I will start taking my
Thank
laptop
you.
out.
Yeah, go ahead and
It's
one
a
more
very
question.
great talk. It's amazing that the earpiece speaker vibration can be captured. So I have a question about, because your type model, you require the user to hold the phone, the victim to hold the phone. Otherwise, I think we can use other technique like a hidden microphone or Wi-Fi to capture the vibration. Because the user hold the phone to talk, so there are speaker sound and the user sound. That the user sound would impact your inference accuracy?
Okay, so this is actually very similar to the previous question, and the answer to that is no, not really, because the real reason is that your phone earpieces are that small, and they're directly connected to all of the solids inside of the phone. They are not damped properly, like larger speakers. So when something is playing, it's like your whole phone vibrates up, and you can try and isolate that signal. Whereas if you're using a microphone, it is, once again going to catch everything in the environment that is being said. Like you could talk or maybe play a loud sound in the background, and that kind of defeats the microphone.
Yeah, I see.
But,
So the
yeah.
radar must point right to the earpiece microphone. Earpiece speaker.
Yeah.
Okay.
Yeah.
Yeah. Thank you.
Thank you.
All right, let's thank our speaker one more time.